Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the new webinar series with academics of the ITU Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our first webinar of the season with Professor Petar Popovski from Aalborg University, Denmark. So please submit your questions via the Q&A channel. We will address them to our speaker during the Q&A session. And after the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner live lessons. So please stay online. Professor Popovski agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm very pleased now to introduce Professor Ian Akyildiz, Editor-in-Chief of the ITU Journal and founder and president of TRUVA from the United States. Professor Akyildiz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. He has established many research centers worldwide, including in South Africa, in Spain, Saudi Arabia, and Finland. He is Editor-in-Chief Emeritus of Impact Factor journals and highly cited at the top of the most prestigious international ranking. Ian is a visiting distinguished professor in several universities around the world. His current research interests are in 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. So Professor Akyildiz, the floor is yours for your opening remarks and to introduce our speaker. Thank you so much.
Thanks, Alessia. Good morning, good afternoon, and good evening. Greetings from Atlanta to our global audience. It is my privilege to welcome you all to the ITU Journal for Future and Evolving Technologies webinar series as we kick off Season 4, Episode 1. Once again, we have curated an exceptional lineup of speakers for the season, and I'm thrilled to introduce our first speaker today. Before I do so, allow me to provide a brief overview of the journal. ITU Journal on Future and Evolving Technologies, in short form J-FET, was established with the mission of bridging the academic and industrial worlds, fostering collaboration and advancing cutting-edge research. The vision for this journal was conceived back in December 2019, and we successfully published our inaugural issue in December 2020. As an open access journal, we ensure that there are no fees for readers and authors, making high quality research accessible to all. Each submission undergoes a rigorous peer review process, and we strive to cover the most timely and impactful research topics at the intersection of academia and industry. The success of the journal is the result of collaborative team effort, and I would like to take a moment to acknowledge the invaluable contributions of Cizo Ono, Bilal Jamusi, Alessia Magliarditi, Erika Campilongo, and Maria, both Marias, and many others. Their dedication, hard work, and unwavering support have been instrumental in shaping the journal into what is today. I encourage all of you to consider submitting your research papers to the journal. Additionally, if you have ideas for special issues on emerging or popular topics, please do not hesitate to reach out to us. Now, it is my great honor to introduce our distinguished speaker for today, Professor Petar Popovski. On behalf of the entire ITU Journal FET team, I would like to extend our heartfelt gratitude to Professor Popovski for accepting our invitation and sharing his insights with us today. Petar is a professor at Aalborg University in Denmark, where he leads the connectivity section, and he also holds the position of visiting excellence chair at the University of Bremen in Germany. He earned his diploma engineer 1997 and a Master of Science 2000 degrees in communications engineering from the University of St. Cyril and Methodist in Skopje, which I visited many times. Her advisor, Professor Lina Gavrilovska, is a friend of mine since maybe over 3.5 decades. And I'm very happy to have her as a friend. And of course, Petar too. And his PhD, he received from Aalborg University back in 2005. A fellow of IEEE, Petar has received numerous prestigious awards, including the RC Consolidator Grant in 2015, the Danish Elite Research Award 2016, the IEEE Fred W. Ellersig Prize Award 2016, the IEEE Stephen O. Rice Prize in 2018, and Technical Achievement Award from the IEEE Technical Committee on Smart Grid Communications 2019, and the Danish Telecommunications Prize 2020, and Willem Investigator Grant 2021, and many others. Currently, he serves as the editor-in-chief of the IEEE Journal of Select Areas Communications, in short form JSAC, and as the chair of IEEE Communications Theory Technical Committee. He has also held leadership roles as a member at large of IEEE Communications Society Board of Governors, and as the general chair of IEEE Smart Grid Com 2018 and IEEE Communications Theory Workshop in 2019. Petar's research focuses on wireless communication and communication theory, with significant contributions to ultra-reliable low-latency communication, in short form URLLC, massive type, machine type communication, MMTC, and Internet of Things. He is the author of highly acclaimed book, Wireless Connectivity, an intuitive and fundamental guide published by Wiley in 2020. According to Google Scholar, his H index is 78, and his work has been cited 33,500 times as a testament to the profound impact of his research. Petar's contributions to the field of communication theory are widely recognized, and he continues to produce high-impact, groundbreaking research. On a personal note, I first Petar many years ago. I have followed his research closely over the years and have always been deeply impressed by both his work, his dedication, and his professionalism. Since 2017, we have collaborated closely to ensure the success of the Balkancom conference. I'm truly delighted that he's now joining the esteemed line of our speakers in our journal's webinar series, adding to its rich history. Without further ado, let us welcome Professor Petar Popovski as he takes the stage to deliver what promises to be an engaging and insightful presentation. Petar, the floor is yours. Thanks again.
Thank you very much, Ian, for the very, very kind introduction, for your kind words. And thank you to you and to your team for inviting me to this webinar. And I'm going to talk a little bit about our research that is related to timing, which is a more general concept of related to latency in wireless communication systems. And I hope you can see all my slides. So the title is Wireless Systems at the Intersection of Physical and Digital Time. And the work done here can be credited to the grant by Vilux Foundations in Denmark, as well as a EU project on goal-oriented communication, which is called 6G Goals. So this is the outline of my talk. I'm going to talk about some trends towards 6G. What are the topics that are of interest? There are many topics that are of interest. I will just touch upon some of the trends. Then, as my focus is on timing, I'm going to speak about modeling of latency. First, only the latency, and then I'm going to talk about how latency gets complicated by using different timing measures. And then, even further, I'm going to talk about what does it mean when we have base stations that are not used only for communication, but they're also used for sensing. And in principle, they are mapping the physical reality to the digital world. So what kind of consequences this has, and what could be potentially interesting issues to consider there. So to start with 6G, basically the 5G had an ambition to be the supermarket of connectivity, right? So basically in 5G, we had this triangle of broadband, ultra reliable, low latency, and massive machine type communication. And then the idea was that once you create this type of connectivity, by combining them, you can create any conceivable connectivity. So that's why I call it a supermarket of connectivity. Well, but as things are developing, in the meantime, there have been significant developments in the AI, and then there has been also trends toward introducing more sensing towards 6G. And if you look into the applications, we see that there is a clear trend towards increased fusion of the physical and the digital world. So if we have that, for example, like in digital twins or metaverse or extended reality, then the question is, what are the challenges that are going to enable this real-time fusion between these systems? As augmenting the domain of 5G, we can say that in 6G we have a localization or positioning, sensing, and all of this is glued to intelligence learning and inference. So you have seen probably many use cases that are in 5G, but here is one that is very realistic, and we got it from our collaboration with the people in health technology. So bionic limbs is a technology that it helps, makes the life easier for many people, and historically they have been mechanical. Then they were made analog. Then the current generation is digital. For example, artificial arms and hands and so on. And we think that the next generation will be connected. So if you make this connected, then the number of applications becomes very large. For example, you can have exoskeleton where let's say disabled people or elderly people are being monitored remotely, and there can be intervention from a medical person. Then there could be computational offloading, in the sense that the prosthesis can, or the bionic limb can try to understand the context of the environment, and based on that upload appropriate software, or provide additional information to the user and so on. So I think it's an interesting case, and it's why it is interesting in terms of real time, because obviously the limb should operate in real time, so should help to people to interact with the world in the same way as the natural limbs are doing, right? So that's why we have seen a lot of challenges here. And in this paper that we have recently published in the Signal Processing magazine, we have kind of made a roadmap and challenges for this type of applications. So in general, we can say that 6G augments the connectivity horizon. And one unavoidable thing is the artificial intelligence and machine learning. And then the question we as communication engineers we can ask is, how are the communication protocols affected by the growing intelligence in the nodes? So we start to have AI in various nodes, various devices. The question is, what kind of requirement that poses to the communication protocol? So if you start from the original Shannon model, the green one, that is a communication theoretic model. Once you add the red thing, this is the protocol information, then you make it into a networking problem. And then on top of it comes intelligence. So I'll come back to this, to the impact of this intelligence on the next slide. Just let me tell about another trend, which was, I should underline that Ian was one of the pioneers who thought about these small satellites and interconnection and supplementing the terrestrial networks with the non-terrestrial network. And this is now mainstream. When I say mainstream, it means that it is being considered in standardization, and it most likely will become part of 6G. And in principle, if you think of what 6G will be, you can say that there could be integrated communication and sensing using a specific spectrum, FR3, or using AI and so on. But what makes difference for the user is whether the user can be connected all the time, for example, being in an airplane and so on. And I think at the moment when the phones standardly get connected to the satellite network, we say that we have 6G. So a bit unavoidable topic is this topic of semantic communication. So this came a couple of years ago. I think we had it with my colleague Osvaldo Simeone. We had it in our talk in the first 6G forum or summit in Finland back in 2019. So what is the essence of that part? So if you look into the 5 language domains, there is phonology, morphology, syntax, semantics, and pragmatics. And if you look into the communication systems, we have a physical layer which can loosely be connected to phonology. We have packets like the minimum language unit that could be connected to morphology, and we have syntax which could be connected to control information. And somehow we have vacuum. And this vacuum on top of it could be in principle filled out because of the growing intelligence of the nodes in the network. So if you look into the introduction to Shannon's paper written by Weaver, he speaks about level A problems, level B semantic problem, and level C effectiveness problem. In my opinion, the growing intelligence in the node, in the network, leads to this kind of concept of semantic and goal-oriented communications, where rather than assuming then that the nodes need to receive certain information, for example, represented by certain entropy and certain bits, what we can say is that we have to maybe figure out what is the knowledge of the other nodes, and then based on that, devise protocol that are going to only transmit the necessary information. So let's go to latency. So latency has been very much into focus of 5G. And in 5G, there were some numbers that were often used, like 1 millisecond. And then you can see some visions for 6G that speak about even lower latency, going to microseconds and so on. But if you do a simple math with the physics, you see that because of the speed of light, we cannot really go below some latency when we have a certain distance between the nodes, right? So I think it's advisable to talk about more general timing in the 6G systems rather than just talking about low latency. So for example, if you look into the Open RAN, they define 3 types of categories. There is a real-time timing, which is below 10 milliseconds. There is near real-time, which is 10 to 100 milliseconds. And there is non-real-time, which is more than 1 second. And this kind of timing has been also adopted by the 5G industrial and automation consortium, 5G ICA. Then another thing that we can speak about latency and reliability is this coupling between them. So when we take a packet and transmit through a communication system, any communication system, so we can characterize it with this curve, which I call latency reliability curve. So this curve tells us what is the probability that the packet is going to arrive by a certain time. So this probability that the packet is going to arrive by that time is increasing as the time is increasing, because as the time passes, then you have more chances to send the packet again, supplement information and so on, so make it correct. But in the end, it might converge to some value, which is 1 minus PE, where the PE is the residual probability of error. So the probability of error, the probability that the packet can never be delivered, right? For example, even in Wi-Fi, after 7 times of retransmission, the transmitter gives up. So if we want to put latency and reliability guarantees, for example, we want that the packet arrives by a certain deadline with a certain probability. You see that by this deadline and the probability 1 minus PE, the blue curve doesn't attain it. So the way to attain it is to go to the red curve, or to lift the blue to the red, towards the red curve. How do we do that? We do that by using diversity. So we have to add a certain level of diversity. We have to increase the power, or we have to put more antennas, or we have to allocate more bandwidth, and so on. So in principle, if you when you speak about latency that you want to achieve in the systems, then you must specify the bandwidth, because the bandwidth is related to the physical placement of the systems in time. So we cannot speak about latency by just looking into discrete symbols. We must speak about the bandwidth. So you see, this latency is directly related to time, and time and space are used to describe the physical world. But suddenly now we have time into the digital world, and then we need to relate these two things. That's why the title of the talk is the timing, which is in the intersection of the digital and physical world. So the latency, as I said, was heralded as one of the main features in 5G. And it has been coupled with high reliability into ultra reliable low latency communication. But you can say that the approach has been maximalist, in the sense that if you look into the total latency budget, there is a computation, there's a compression, there's a core network, and then there is 5G. So what the approach has been, okay, let's cut a small and predictable piece of the overall latency and allocate it to 5G, and let it be, for example, 1 millisecond. And then everything else could redistribute the latency budget depending on the application. I mean, this is a good system approach, because then you have a system that has a predictable performance with certain reliability, but is not good from other perspective, for example, from a perspective of energy consumption, because if you have a system that is always ready to deliver with 1 millisecond, that means that this system should be clocked and computing at a very precise rate, and then spends a lot of energy, right? And then there have been related considerations within 3GPP, for example, about different timing measures and latency measures and so on. But let's look at a very simple model about the total latency budget, about the total time it takes to transmit a packet. For example, 3 generic operations are computation, compression, and communication. So if you have a data packet, D1, then it goes to a computation, then it's put into compression, then communication. Then this is the total time it takes is T1 plus T2 plus T3 from different components. And then in this first model, the processing time depends only on the data. So you can say that the time, if these are random times, they are independent between the 3 modules. Another model could be where we can couple, for example, the processing time of the computation and compression. So we're using the same processor, and then this processor for computation and compression is kind of sharing the time, prioritizing these processes, and so on. So T1 plus T2 are not independent random variables. Or we could also just take the computation and compression, make them inseparable, so completely coupled, and then take a communication as the next model. Or even we can couple all of them together. Point being that in this case, we have some random variable, and we have different levels of dependencies between them. The nice thing about these random variables is that the expected value is a linear operation, so it's a sum of the 3 expected values. So this is easy. The problem is that you want to give certain reliability guarantees. So you want that the total time is less than a certain tau. And this has non-trivial relation to the other CDFs. You cannot combine them simply as the expected values. So here, when we speak about the end-to-end reliability, is not only that the communication may fail because of the error in the packet, it also can mean that the compression is not finished by the deadline. And the compression cannot be finished by the deadline because the computation might take a random time. And why computation takes random time? Because the computer is also doing something else, right? So, so basically, we are combining 3 different CDFs in order to find out what will be the final CDF. And then this coupling between different variables, which I mentioned in the previous slide, is important because that will decide how these 3 CDFs will be combined. So we have, together with the people in health technology in my group, some time ago, we have actually tried to look into the total latency budget. And the total latency budget, for example, for a closed loop control, we have a human operator that operates robotic arm in a remote environment. So we want to find what is the total amount of latency that goes on the data transmission, processing at the mobile edge, compression at the robot, decompression, execution of command, and so on. And then to make this, we have made a very detailed model. We have assumed that the variables are independent, not coupled, as I mentioned before, which could be also added as a next step. And then we have assumed that they're independent, and then they're connected only through the data size. What does that mean? That conditioned on the data size, the two variables are independent. This would work well if each of the operations has a separate processor. But in principle, in ORAN, they are sharing common computation resources. So there is an independence between these variables. So it would be very interesting. If you're looking for an interesting topic, it would be very interesting to see how you could model this type of dependency and latency in ORAN where the processing power is shared. And we have looked into two cases where the robot compresses the data and the robot doesn't compress the data. And then there is a fundamental trade-off there. So the trade-off is the following. If you have compression and communication, you can spend time to compress the data. So if your latency budget is, let's say, 10 milliseconds, you can spend your time to compress the data. Let's say you spend 7 milliseconds to compress the data, but then you have only 3 milliseconds to send it. Or you can spend less time to compress the data, so compress it less, you can spend 2 milliseconds, and then you have 8 milliseconds to send it, but you have more time to send it, but even you have more data because it was not compressed. So we have looked into what is the optimal compression ratio, and for example, for different types of processors. And obviously, when the processor is stronger, like 5 gigahertz, so the optimal compression ratio is higher because we can compress the data quicker and send less data, right? So this is an example how a computational power is used to make the communication more reliable within a given deadline. So another thing that how we have modeled it is that we have to model the computation, we have to take a model of the processor where we say that the time which is taken is proportional to the data size of the data. Then there is a random variable, which is gamma distributed, and then there is a processor frequency. So if the processor frequency is higher, then the time required to process the data is lower, but this is not deterministic because it depends also on the random variable. And the thing is that there is the power that is consumed is roughly proportional to the third degree of the frequency. This is actually only approximate because there have been empirical studies that show that the power is approximate to f to some other degree, but it's not linear, definitely. And so the energy consumption, very roughly, is f to the third degree multiple d divided by f. So basically, the energy consumption increases with a second degree of the frequency. So this means that low latency requires fast information processing and induces energy cost. So that's why URLC, if we always go for 1 millisecond, would consume a lot of energy. So the question is how to optimize all these things. So we have several variables here. We want to meet certain latency. We want to process the information with certain accuracy, but we also want to spend less energy. So it's impossible to minimize everything, to optimize everything. There is of course a trade-off there. And then we can also ask the question, okay, what is a latency that is good enough? And then we have studied experimentally with human subjects. We have studied what is a closed loop depending on the task that we were getting. For example, the task was to control some trajectory of a ball on a screen using a joystick. And there were two types of inputs. There was a visual input or tactile input on the joystick. And then we have looked at the 150 milliseconds was quite okay. What we have measured the correlation of how well we are tracking the ball depending on the latency and the error that appears in the channel. And the performance was affected by average latency, but not by random latency fluctuations. But the most interesting thing that we have observed here, which when I say it now, it's obvious, but is that when we were increasing the latency at some point, so we were having a task of controlling some ball, and then we were increasing the latency, and the human subjects were not at the beginning good to control the ball, but by time they were becoming good, because the human uses intelligence and the predictors. It doesn't need the communication, right? Because who predicted where the ball is. So in order to find what is the impact of the communication, we had to design a task that is random. So we had to move the ball randomly as much as possible, unpredictably. And in that case, the humans could not really learn it. So that then it depended mostly on the communication through the visual and tactile input. But the conclusion was that the control with visual feedback was always better than compared to the tactile feedback. So the coordination was much better when the visual feedback was delivered on time rather than the sensory tactile feedback. Okay, so this was about latency, and we have shown some even experimental results how latency affects these cyber physical systems. Then how latency gets complicated. So instead of looking at the latency, in the last 15 years, there has been interest in another measure, which is called age of information and its byproducts. So age of information is suitable for tracking application or sense, compute, actuate cycles, and so on. And the interesting thing in age of information is that we are removing the assumption from latency, where the latency says the packet is there, you have to send it. In the age of information, we also consider the sampling moment of the packet, meaning that we say, when is the packet generated, how old is that information, and when is that information received at the destination. The key assumption is that the fresher information carries more relevance and has a higher effectiveness, for example, stability in a controlled system, or presents a more meaningful picture of the current state of the affairs. In other words, what the time passed since the information was generated is a measure of how well we are perceiving the outside world. This is again at the intersection of the physical and digital worlds, because this is a simple measure that tells how accurately we assess the state of the world based on when the information was sampled and when it is delivered to the destination. Then we have done some experimental work on this with our collaborators in Bosch, where we said, okay, this idea came from the fact that our PhD student at that time in Bosch wanted to measure the age of information to find out which age of information is sufficient to, to have this control of an inverse pendulum, and also or controlling the trajectory of a robot or of an automated guided vehicle in a factory. So we wanted to find what age of information was sufficient in order to achieve stability of this trajectory tracking and so on. And then it turned out that it's very difficult to measure the age of information because you have to have perfectly synchronized sender and receiver. And then we thought what to do about this, and we said, okay, why don't we measure the age of loop? So instead of the sensor measuring the age of information, so the robot samples the state of the world, sends it to through a wireless network to the controller. The controller computes the action and sends back the actuation. So it's a kind of round trip time, similar to the round trip time, but it involves the moment of sampling the sensor. So we have to decide when to sample, depending on our state, to ask for help from the controller. So we can say that what age of information is towards the latency, that is age of loop towards the round trip time. And so what we have done here is we have used some reinforcement learning to optimize the loop rather than putting a latency requirement. And this is very indicative for something I mentioned before. This is telling us how much bandwidth it requires to keep the system stable. And for example, if we want to guarantee 1 millisecond an uplink and 1 millisecond in the downlink, then this is a very strict requirement. We have to use a lot of bandwidth. But if we train the reinforcement learning scheme that learns what is the state of the system and optimize the entire loop timing, then actually the bandwidth is very small, because this is kind of a goal-oriented communication, an example of goal-oriented communication, because the goal is to keep the system stable, and you do not just indiscriminately reserve 1 millisecond in resources, but you're saying, okay, I'm going to use the communication resources opportunistically as much as is needed to control and keep it stable. Then another thing that this could be generalized is to borrow some ideas from computer science, especially from that database, where we can speak about push and pull based reading or push and pull based communication. So if you think from a database point of view, Shannon's model is a push-based model in a sense that we have an information source that generates the data, and then the receiver is certainly interested in the data. So this data is relevant for the receiver has to receive it, it has to be correct. So that's what Shannon's model. There's nothing bad in that, but just if you take the general view from the database, this is called permanently subscribed the user to the sender. So the receiver is a user that is permanently subscribed to the sender and wants to get everything that the sender generates. Pull-based communication is a bit different. So in a pull-based communication, the receiver asks the sender about a specific data, asks with some query, asks some question, and if there is a relevant data, it will get answered, right? So pull-based communication, you can think in satellites where data is pulled from the ground, or it could be cloud-based queries to the edge devices, data fetching in a control loop, and so on. So in that case, in pull-based communication, the age of information can change meaning, because here we can speak about query age of information. So we do not want to average the age of information over all times. We just want, whenever the query arrives, the information that is delivered to this query to be fresh. So previously in the age of information, we are optimizing the average value of age of information of a continuous process. Here, there is a query moment, and then we want to make the information fresh when the query arrives, when the information is read. So the key question here is how to organize the transmissions so that what is received is very fresh at the time of reception. So that means that the trade-off you can think in the following way. If I know that the query moment is in 10 seconds, then if I sample the data now, I have 10 seconds to send the data. And then the reliability of sending this data will increase over time because I can retransmit, improve my power, change the frequency, and so on, and the data will arrive. But the data will be 10 seconds old. On the other hand, if I sample the data 50 milliseconds before the arrival of the query, the data will be very fresh, but I don't have time to send the data, right? So the question is, what is the optimal one? Then, I mean, there is, of course, mathematically, this problem becomes a discrete optimization problem compared to the case of the mean value of age of information, which is a continuous variable optimization. Then, speaking about latency, one thing that is interesting to mention is the generative AI. And this is also a bit inspired by this thing which I mentioned before of users that were controlling the ball by joystick and then predicting what is happening. So you can think in the following way. Traditional communication systems, the destination needs a packet replica. So the traditional routing is just replicating the packet around. And then maximum sending rate is given by the minimum cut of the network. And caching can help, but all data is still transmitted. So think about generative AI. You have a node in the network that is capable to generate data. And this data can be generated by sending prompts. So, but prompts should be understood in a very general way here. For example, if a source wants to send something to the destination, then the source sends the packets one by one. And if some packet doesn't arrive or is too much delayed, then the generative AI can actually predict what this packet could have been, because the generative AI maybe has a very good model of the source and sends it to the destination. So this is not violating the principles of information theory. It's just telling that the entropy of the source is conditional on the knowledge that the generative node has about the source. So if we have a large learning model that knows what the source would send, then it could try to predict it. This is related to latency very much, because if we can quickly generate nodes intermediately, then we are reducing the end-to-end latency, because we do not need to wait for the packets that are perfectly predictable. So the principle is that if it can be predicted, it does not need to be communicated. And I think the use of AI into predicting what can be sent And again, in the Shannon's model, we have an entropy of the source, and the assumption is that the destination has this full entropy of the source. Basically, the destination is fully ignorant about the source with an amount of uncertainty equal to this entropy. But in practice, we have to know what we don't know. So, right? So we have to discover this knowledge. And this is where some of this predictive generative model could help, because we could have an initialization phase to figure out what we know about the source. And then the generative node is a kind of like an entropy bridge between the source and the destination, where it just delivers to the destination what the destination doesn't know about the source. So finally, my final part is related to the physical versus digital time. And let's look into the time in the physical and digital world, in the fused physical and digital world, that is through an example. We have a base station and a robot, and then we have an event that happens. And this event is acoustic, some explosion or some loud sound. And then this acoustic signal that is spreading with the speed of sound, right? Then this event 1 is causing event 2. And then this basically is also registered by a certain sensor. So on the other hand, the base station has a radar sensing. And we have a user that is also capable to sense some of the data, observe the data, right? And the blue one is the data communication. So what happens is now that the physical process, the event 1 happens, and the event 1 happens, when the event 1 happens, is sensed by the sensor, microphone next to it, and the sensor is digitalizing the data and sending it to the base station. So it arrives as an event, digital event DB1. On the other hand, the event, the physical, the robot has a microphone and is sensing the acoustic event directly. So it arrives as a sensing event SR1. Then the event E2 is sensed by the base station, which could be, I don't know, opening of a door, turning of a car, or whatever. Then the event E2 is sensed, and so it comes after the event DB1. And the robot, the robot senses the event SR1. The robot gets the event E2, information about the event E2 from the user Z, which means, and this was processed very quickly, and then it comes before SR1. So you see, now the event E1 caused the event E2, but here the base station receives them in one order, the robot receives them in the different order. Then you would say, okay, this is not a problem. You would just timestamp the event. Then, yeah, you would do that if you have entirely digital world. But here we are speaking about fusion of physical and digital world. And in the same way in which we observe reality without using timestamp of the reality. So if I look outside my window, I know what happened before what based purely on my perception. I don't need timestamps of those. And why I need that? Because my brain and our brain knows how to interpret causal events. But if we have base stations and cyber physical systems that are equipped with sensors and data, we have mixed digital and sensing information, then this could be a problem. So the chronology depends on the observer and data processing. Okay, when we say that the chronology of the event depends only on the observer, then we are replicating a very famous theory, which is the theory of relativity, which says that it doesn't make sense to speak about simultaneity of events that are not collocated. So because different users will observe different chronology of the event. But the causality cannot be changed, and causality is decided by the speed of light. Inspired by this, in '78, there is a seminal paper in distributed systems by Leslie Lamport, who, by the way, is the guy that created LaTeX. And this is about time clocks and the ordering of events in a distributed system. Very much inspired by theory of relativity. It tells how to put timestamps in digital systems in order to order the events in a distributed system in a consistent way. Of course, this work was follow up. There was some improvements of this system and so on, but the basic idea is great here. The point in these two systems is that in Einstein's system, there is no time for processing of the events. Everything is instantaneous. While in Lamport systems, he also doesn't consider the processing time, but he also only considers digital events. Now let's look at our setup, where we have mixed physical and digital events. So if you look into the theory of relativity, we have this light cones and causality with the instantaneous information processing. So for example, as Einstein's theory says, that we cannot inverse the causality of the events because of if we process them instantaneously, then we know that they have to occur in certain order. I mean, pushing a car will result in a car moving. Is not that the car first moves and then the push comes. I mean, all the observers should observe the same thing, that the pushing of the car is a cause to it. But when you add time for processing the data, then this becomes uncertain. For example, here we are adding the processing time. We have a sensory time of one event, and we have a time for receiving the data of the other event. So in principle, if the data rate is low, the time for receiving the data is large, and then we might receive this in a different order. So you can say, okay, this is not a problem for digital systems because we can synchronize them perfectly. And then we can put timestamps that are perfect. And then based on these timestamps, we can always order them accurately. That is in principle correct, but ordering them, synchronizing them perfectly puts a very strict requirements on the clocks and very high energy expenditure. So in principle, you would like not to be synchronized too much. You would like to have a relaxed timing environment, timing requirement, and then you would like to save some energy, right? Okay, so then let us look into some inspiration from humans or from living beings. So how do we make sense of a space-time? For example, auditory and visual stimuli arrive at a different speed. If I clap my hands now and look at them, there are three stimulus there. There is a auditive one, there is a visual one, and then there is a tactile. And all of them are arriving at different speeds, and there are different processing speeds. However, the brain plays them out after synchronizing their output. So basically now is defined by this processing outcome. So every time we say now, that's 150 milliseconds in the past. And the simultaneity for us is determined by what was evolutionary important. So there is something that is called horizon of simultaneity, meaning that it's like 10, 15 meters. So within 10, 15 meters, our processing is done in a way so that auditory, visual, tactile stimuli, they can be perceived simultaneously if they are related to the same event. But for example, if the thunder hits 3 kilometers away, then we are going to see it first and then hear to it. Why? Because this was most likely, I'm not expert in this, but most likely this was not evolutionary important. So it was not evolutionary important for thunder that is 3 kilometers away to be perceived simultaneously with the light and the sound, because it's not part of our horizon that we interact with. Okay, now there is a trend in the recent years, and also with 6G, of putting perceptive mobile networks, meaning that combining sensing and communications in the network. And this motivated me to write this paper about time, simultaneity, and causality in wireless networks with sensing and communication. And again, the problem is because of the sensing, because the sensing is a way to convert the physical into the digital world. And this is where we have to get the time right. And for this, I looked into some inspiration from multisensory integration in the science of perception. And basically, the humans are using these windows of perception or temporal window of integration. And everything that comes within a certain temporal window of integration is considered as a now. Then I tried to analyze this by making a very, very simple model of a synchronous sensor. So a synchronous sensor is the one that starts synchronously and then at the output at the end outputs a result. Or then I have a model of a communication data, and then the integrated process is mixing the sensory and digital events. So so by adding temporal windows of integration, we are trying to make some events that are to be simultaneous. The larger the temporal window of integration, the more events are simultaneous, but then the lower our throughput of the events. So what could happen? For example, it could we can have a situation of causality violation. Causality violation means that the event E1 caused the event E2 in the physical world, but the way we have perceived it and stored it in our system, it turns it around, right? So it says that the other event caused the first one. So here is some system for analyzing it. So when you're analyzing it, we can try to find the condition how to put the temporal windows of integration so that in a way we have a chance to avoid the causality violation. And for example, we have here acoustic propagation and radio propagation. And then we can see that the minimum window for integration should be larger than some of these constants for processing the data. And I think our organism evolutionary has optimized these constants, depending on the events that we have perceived. But what we have not done, if we have not account for the fact that the time for action could be negative as well, because if some action could be predicted, then it could be sent in advance. What I'm trying to say is that imagine, it's a bit dystopian future, but imagine a future where events in the physical world can be fabricated as digital events and sent to us. Then we perceive them in an order in which they never happened. And this is because if the time for generating fake events is low, then we could create a reality, for example, that is totally deviating from the true reality. And why this could be important? Because in the future, when we have increased fusion between the digital and physical world, if, for example, an accident happens, we want to go back and look into this event, look into the logs. But what if these logs are showing opposite of what was reality, right? Today we are using witnesses. In the future, we are going to use increasingly more automated and digital data. So as I said before, the larger temporal window of integration leads to a lower probability of causality violation because everything will be taken into the same moment of happening, but it also decreases the event throughput. Then you can say, okay, is this okay to dimension like this? We have seen this in, for example, in OFDM, the guard interval is dimensioned with respect to the size of the environment where we are going to use. For example, in Wi-Fi, we say, okay, this is the range of the Wi-Fi, this is the propagation time, let's put this to be the guard interval. So in similar way, we can actually design these combined physical and digital systems by putting a temporal window of integration. So what I'm aiming here to say is that the base stations might start to operate like our brain, where they deliver the data within certain temporal windows. So I have considered also the opposite case where digital causes a physical thing. But let me also mention another one is that the problem of simultaneity violation. So if some events occur simultaneously, for example, but if let's say we have n observers of an event that happens simultaneously, but then the base station is perceiving them and not being simultaneous and being sequential, then we have simultaneity violation. So this means that it takes a lot of time for all the events to arrive, and the temporal window of integration is short, then this will be considered as a causality violation. So why is this important, I believe? And we are still investigating and thinking about this. I think that you can see the base stations as the guardians of the intertwined physical and digital time. So they are going to orchestrate timing performance of communication and sensing. And they are going to put multi-input constraints for real-time applications. So instead of saying 1 millisecond, we can also say, okay, what this application wants, by which time this application wants this input to make the correct decision. And based on that, I'm going to put the scheduling constraints, schedule the sensors, schedule the sensing of the base station, and so on. But also it could be used post hoc as a temporal forensics. Something that I mentioned before is that if we have, the AI starts to penetrate more our devices and our world, we believe that there is a need for trustworthy base stations that are going to put the correct order of the events. Otherwise, powerful AI might manipulate what is real and what is not. And from a purely technical point of view, what is there for us, for communication engineers? I think there could be new types of problems that are setting the latency and timing requirements for a service. this example of this goal-oriented communication. Something that we are working currently on is investigating the fundamental trade-off between the latency, energy, and accuracy. So it's easy to say that you just have a latency requirement, but in the end, well, if you want to mimic human intelligence, there is a certain trade-off between the accuracy, energy, and latency of doing the task. Like that's why probably we are not reading theory of relativity late in the evening. The timestamps can be inputs for inference further in the network. And if we have multi-user systems, we can define a new types of resource allocation problems. And then we can allocate the resources in order to achieve a certain correct timestamping and decrease the probability of causality or simultaneity violation. So this is the first step, but I think it's necessary to connect it to the intelligence because our brain uses a deeply rooted knowledge to compensate for external factors. So if our brain thinks that something is not causally correct, it corrects it and presents it to us in a causal way. Then brain might be flexible and change its temporal window. For example, if the brain changes the temporal window, it perceives our reality is perceived with certain throughput, right? With certain rate of events. But if we're interacting with machines that are more capable than us, have higher throughput of events, then we have to probably adjust the temporal window, or the machines have to adjust it to us. And then the brain actively shifts the time to compensate for gaps because the brain works with a model and then just tries to fill in whatever was missing was not received correctly. And where have we seen this before? Who has been using this kind of manipulation? Obviously, it was the magicians, right? Because they are using this fact that we are perceiving the world in a certain way, and they make illusion of some other reality, which is basically cheating our senses. And this is okay for a performance and for fun, but imagine a future where we have a powerful AI, interconnected networks, where somebody is changing what happened in reality. Then we need to be able to think at least about the consequences of this, right? So how will the magicians of the digital era look in 20 years? So this brings me to the end. As I said, 6G is on a route beyond communication, and is looking for meaning. That's why we talk about goal-oriented and semantic communications. And we need to look into the actual use of the transmitted data, and we need to look into the integration with the AI. The timing performance depends on multiple components, and the packet transmission latency is just one instance of timing. And I've tried to scratch the surface on the problems of timing when we intertwine physical and digital worlds. And maybe the base stations will be, let's say, the units that are going to deliver trustworthy physical data into the digital world in the coming years. Thank you. You're muted, Ian. I cannot hear you. You're muted. We cannot hear you, Ian.
Can you hear me now?
Now I can hear you, yes.
Again, thanks a lot for the excellent talk. And unfortunately, we have only one question, and I will start with that, and I will ask my questions, and I hope in the meantime we'll get some more questions. The first question is from a person, his name is interesting, York Earwaker, so hope it's a real name, but anyhow, so he's referring to generative AI. He says, general, the base station is general AI brain. And then he says that it's like what you were saying is reference data and only sending the UID, not the data. The edge server has the data, which forwards the data related to the UID.
Mm-hmm.
So good luck when you...
This is in principle correct, that only you can say, if you can predict everything about the users, you just need to send the UID, but this prediction will never be entirely correct. So you always need certain type of verification. I mean, just to go upon this, that the Shannon's model, again, is a masterstroke, just to enable us to mathematically analyze the system. But we can say that the conversation between the intelligent beings is never like that. It's never unidirectional. For example, if I meet Ian for the first time, we try to have some initialization protocol, find common knowledge. And after that, I will not explain to Ian what is a bit and what is digital, because I figure out that he knows all this, right? So I have to adjust my model based on the interlocutor, right? But in the Shannon's model, this initialization phase is removed. They made this initial conversation has taken place, and now everything that I have to say, Ian doesn't know. That's the assumption. But in reality, you have protocols where this is different, right?
I start my question because there's nothing in the meantime. So when I heard about age of information, like almost over 10 years ago, I really thought about the Leslie Lampert's work in the 70s and 80s, let's say 80s, right?
Yeah.
And that's why I really thank you for pointing out here, because many network communications people, they just ignore it. So that's why I never got interested in that age of information, because I felt that like reinventing the wheel. And with different notions and different namings. So and again, you mentioned it here. So what is your take on this? That is it really like reinventing what Leslie, because there were many papers in operating systems and database area, when those people
Exactly
will hear these, they will say, what's going on in the networking community? So so what is your take on that, please?
Yeah. Actually, you're totally right on this, because I also went after reading the Age of Information, I also went to read a bit about the freshness in databases. And these people have been working with these issues for a long time. And even Leslie Lamport is above that, because he speaks about consistency of
integrity,
and
data
integrity and so on.
Yes. Yeah.
And so on. And then I read about this, and I thought, okay, what is interesting to say there? Because he solved, I mean, he didn't solve completely the problem of timestamping, because there was also some issues. Some people after that proposed some vector clocks, matrix clocks. But the idea was his. But I think what motivated me was the fact that when you digitalize the physical world, you must use sensors. And these sensors, they have to take into account the time that it requires to generate the data, the propagation time, and the time that to output to give the output. And if you see how the brain does it, the brain figures it out. I mean, put some temporal window and says, okay, acoustic data, fast processed but slow propagation. Visual data, fast propagation, slow processing. Let me melt everything into the same. So now if you have a future base station that has radar, LiDAR, communication, microphone, how should it present the data about the events that observed? And if you use the timestamping as a source, you can always use the Leslie Lamport's thing. But if you take into account how much the data is, time it takes to process the data, and the fact that the sensory data is not timestamped by nature, but is timestamped by the receiver, then it becomes a bit interesting. And we come to what I was talking about.
Yeah, but also when you look at some realistic applications like these, you worked on smart grid, so they're very, very conservative, as you know. So they will not rely on wireless sensor data to control their smart grid, because it's a very delicate application. So, and also this many other real-time cases, like that's why a lot of people are still working on URLLC, because these latency requirements are really a beast. And I don't think that age of information will help that to beat that latency problem. We need to find some other ways of addressing this. But it's my personal opinion. That doesn't mean,
I think that the latency, as I also tried to point out here, maybe the latency should not be seen separated from the intelligence. So how much intelligence and knowledge is there? That's why I mentioned that these human subjects, the trajectory was predictable. They were learning it, and they could easily control it. And once you give something that is not unpredictable, then they cannot do it.
Yeah.
So I think pure latency. You're right, and this was also probably what I tried to outline, that you cannot see it in isolation, because if you put latency to be 1 millisecond, that would mean that the requirement for computing is a lot on resources. You have to be alert all the time.
True.
Basically, you have to keep your concentration as if you are teaching a class 24 hours per day. You cannot do that.
Yeah. There is another question from one of my grandchildren, Hongji Guo, University of Nebraska-Lincoln. He says, when the network has significant latency, I think latency requirement, prompts are sent instead of source content, and generative AI can be used to generate contents. How do you ensure that the prompts are effective and the generated content has high fidelity?
Exactly.
Creating these prompts may cause longer computation latency. Good question.
Great question. Great question. So currently, I think that the current level, some of the prompts, they cannot be generated as fast to replace the latency. So we can look it into perspective. For example, in the future, when we have faster algorithms and so on, I don't know, DeepSeek 3.0 or whatever.
Yeah.
What happens is that we have to find a way to verify that the data at the destination is not maybe entirely correct, but it's acceptable. So to be acceptable, we can use something like inception distance and so on. So we are not using a minimum square error, but we want to send a picture of a person, or we want to send a picture of 10 people, which is sufficiently well representing the situation on the street. Because on the street, you do not look into the identities of all people. You just know that there are some people, 10 people here, or 15 people here. There's a pedestrian and so on. So you want to represent the situation that is relevant for you. For you, for example, as a driver, it's not relevant probably what is the identity of the people, but it's relevant that there are people. You have to be careful how you're driving.
There is, I'm waiting for another question, I hope. But in the meantime, I will ask you another question, if you allow me. So I really like this concept that you are trying to tackle, is the physical time and digital time. And you try to, come from this Einstein's theory and then try to point that out. And hopefully that will be a very impressive work also when you continue to dig in. So now my question is, when I listen to slide 35 and slide 38, if you can show that to us, what reminded me is, so when we did this multimedia communication in the 80s, and we tried to address the problem of synchronization as well as jitter problem in these multimedia traffic types, we did some buffering in the source. And even for the rescheduling or reordering, we did also buffering at the destination.
Yes.
And then, of course, the question was, how long can you wait for buffering? Because, when you buffer too long to smooth the traffic, as well as at the destination to reach the, avoid the jitter problem or synchronization, you had certain time frame, like you have this time window here, that, without violating those real-time effects. So what is your opinion about this, like comparison to the past and now as your novelty from this perspective? I like this heading now, digital time versus physical time, but the solution that you're suggesting, what is the exact novelty compared to what I described to you?
No, there is probably this is not really a solution, and it's not. There is no novelty in the solution. It's more of a posing the question.
Okay.
And respect to sensors, because you are totally right. And actually, we are citing this. What I'm citing in the paper, I'm saying that this kind of techniques were used in game networking. So the games are doing this because they are waiting for the outputs to come in order to actuate certain situation. So this is not. I mean, these techniques have been used before, and also it's a good example what you mentioned in multimedia. The question is here whether. And that is within some digital, after things are digitalized. The question is here whether when we have base stations deployed in the wild, whether we should apply this system in order to embrace the physical data and with which throughput we are presenting the physical world. Because, for example, the throughput of the physical world perceived by me and you is evolutionarily determined by what was important for us. But we can make a machine that is perceiving the world to a much better detail than us, right? Like this fast shutter cameras and so on. It was just not important evolutionary for us. The question is, what is important for a base station? How it should register the events, how it should deliver the events, you know, whether there would be a conflict with, if the base station is deployed at a traffic crossing, what should be the resolution of the event so that we can actually decide what happened at this traffic light.
Thank you, Peter. And there is another question by Mahmoud Abu Amar. His question is, if an intelligent node is able to interpolate missing packets or packets in general, does this also mean that compute plus compress plus communicating latency should be jointly considered?
Excellent question, and I will respond with a very simple thing. Let's take you find one of these puzzles online. So you have two options. You can think carefully, compute, or you can call your friend who solved the puzzle and he can tell you the solution, right? So, so it is the same here, that if you want, the more precise you want to make the reality, you can probably invest more computation resources and latency in that. And the question is whether you want to do that or you want to that the data is sent to you by somebody else. And the question is always, of course, the assumption in the Shannon's model, I always come back to it because I think it's a very important one. The assumption is that there is a entropy that you're not able. There's a signal with the entropy, so there's certain truth there, certain process that you cannot compute simply because you are perfectly uncertain about it. That's the definition of entropy. It's aleatoric uncertainty. But if that is not perfectly, basically, if you have certain knowledge, but you have to dig it out by computation, then you can actually figure that out. A good example is a mathematical proof. Mathematical proof, looking from an information theory point of view, has zero information because there is nothing random there. You start from a statement, you prove it, and you deterministically come to the end. So there is no information in that. But there is a processing how to transform the original statement into the final proof, right? So this is the example of something that maybe you can compute, but if you don't want to compute, you can get it communicated from somewhere.
I would like to add something else that, you know, when you talk about all this processing delays, then we really need to reconsider the TCP/IP protocol stack. And Huawei was trying to address this, but somehow, of course, they are vetoed at ITU and you know, other forums, because with all these protocol stacks, it will be extremely challenging to reduce the latency. You know, we already have the you know, physical layer like propagation delay, etc. But then when you go higher layers like MAC routing and even TCP, good luck, right?
Yeah, exactly.
You know, we had also like in these 2000s and 2010s the cross-layer protocols. I'm sure you remember that.
Mm-hmm.
They try to reduce the overhead of the protocols, but still, I think we need to eliminate more. You know, I hope that the younger generation will look into that. Otherwise, we'll be just dwelling around and, you know, having another vitamin without solving the problem. So that's my opinion. But anyhow, so let's go to Sadvik. So more questions are coming. So we have to really converge to the end. So Sadvik Boddu is asking, in the latency part, when talking about a cascaded system and trying to merge, say, different modules together, in what way were you expecting the combination to look like? Is it something like cross-layer approach? I just mentioned about cross-layer approach without reading this thing. What I was trying to understand was when we initially built the modular approach, the bigger idea was to have each block independent. Yeah, I mean, we just talked about, I just mentioned the really, bravo, Sadvik. So that we could optimize each block. So combining blocks again seems like we are regressing. Sorry if the question seems ignorant.
No, I think the question is
ignorant, but anyhow, yeah, go ahead.
The question is great. So also back also to what Ian said about cross-layer optimization before. I also worked before on that. Cross-layer optimizations, and also here with different modules, is a great idea because it tells you how to optimize a specific thing, for a specific setup and so on. But the success of internet is architectural, in a sense that it gives you architecture that can address anything. Not all of this is, for each of these problems addressed by internet, you can find your perfect solution, which is cross-layer. But the internet is giving you architecture based on different modules. So the point of different modules is the following. When you, if you merge for example, the modules of communication, compression, and so on, then you have a single provider that is selling the base station, right? And this provider can optimize them, optimize the processing time, and so on. And then you're getting a distribution that is joined over these times. I hope you can follow me, Sadvik, the one that asked the question. But when you take open modules, then what you do is you connect them, interconnect them, and they interact only through the interfaces. Then I don't remember who was exactly, but said, okay, maybe when you optimize your closed base station, it will be great for some services. But when you have an open system like the internet or Open RAN, it can adapt to future services that you could not anticipate now. So maybe in a specific situation, it will not perform very well, modules, but it's able to adapt to different cases. And you are sacrificing performance for architecture. So you just have to be aware that when you have different components, that each of those components have latency that is perhaps not controllable. It's given to you. But when you couple components, you can decide where to invest, where you can invest computing power more into the compression rather than computation. I hope this was clear answer.
Thank you. Now we have two more questions, but the time is really up because Alessia will have questions for you. I don't know, Alessia, shall we take those two questions or you want to jump in? I have to apologize to York and Gordana because they have two questions.
Yes, Ian, maybe two questions definitely with quick answers if agrees.
One question is kind of open-end, but I will ask. I asked Gordana's question first. It's a little bit too wide. Can you comment on the complexity of digital twin implementations for medical applications?
Oh, yeah. I mean, I'm not really the expert in general in the medical applications, but what I have seen from working with people in health technology is that the digital twin should definitely not follow the 1 millisecond thing. And obviously the temporal constant of a human interaction has to go to be above 100 milliseconds. And then maybe you can base the system on that. The key point is to understand what are the minimal inputs there and what is the energy consumption to keep this synchronized in real time. And as I said, we have done this with the interaction with the robotic hand. So robotic hand was in some sense reflecting what the real hand was doing. But for monitoring as I said, the overall situation in a medical sense, I think we need to find what are these temporal constants, and I think they are quite long. I mean, it's not 1 millisecond.
Yeah. We can talk offline at Balkan.com conference. So sure. Another question is again by York. He's a little too short about his questions. How predictable is the event? I don't know what he's talking about, which event, but anyhow, High predictability means generative AI can interpolate, make an educated guess. High entropy events means hard to interpolate real-world data, as generative AI educated guess, he says.
So again, I will come back to the definition of entropy. It's to the very basic explanation, I would say, because that will probably clarify this. So in Shannon's model, the receiver B has uncertainty which is equal to the entropy of A. And that's the entropy that cannot be predicted. So that's why we have to take the entropy of the variable A, XA, let's call it, and the amount of information we send it is equal to entropy of XA. However, B might have a knowledge about A. So the real thing that should be sent by A to B is entropy of XA conditioned of the knowledge of XB of B. But the knowledge of B is not known by A. So A can only estimate the knowledge of B. So that's why it's sending the entropy of XA conditioned on the estimated knowledge of HB. And this is the place where the generative AI can enter and say, look, your estimation of my knowledge was bad. I can predict more than you think about me. And that's how it can be done.
Okay, thanks a lot. And I think we close the Q&A section or session. And Alessia, please go ahead and ask your questions or live lessons from Peter. Thanks a lot again. And we'll be listening to your experience and your advice.
Thanks a lot for the great questions.
Thank you.
Thanks a lot, Ian, for moderating this very interesting Q&A session. And thank you very much to our speaker for your excellent presentation. So let's move to the Wisdom Corner. Live lessons, which aims at offering a unique and special angle to this series of webinars, adding a personal touch. So I would ask you my first question. Looking back on your journey, what is the most valuable life lessons or even a failure that you have encountered that shaped your path? And how can this lesson inspire or guide those attending the webinar today?
Yeah. Probably there are many lessons and there are many failures. I mean, usually when I'm asked to give this presentation for young professionals, I start with a slide that shows how many grants I got rejected and how many I got accepted, and it looks very bloody. The red is the rejected, the green is accepted, and you just have to work with the failure. But I think one of the most important thing, which I've not seen elsewhere, and I'm usually telling it, is to cope with the negative determination. What is negative determination? For example, you start in the career, you learn, you study, you get good grades, and then people tell you, well, grade is not everything. You have to start to publish. Then you start to publish, and then they say, well, you're publishing, but you're not publishing exactly the journals I think are good. Then you're making some papers, and they say, well, your papers do not have math as I want it to be, right? So everything is negative determination, right? Saying you what you're not doing. And then they say, okay, you are published, but you're not very cited. Then they say, yeah, but you're very cited, but your citations are not from this journal. In the end, when you listen to people telling you this, the end statement is that you are not like me. And actually, you should not be like them. I think your definition is at the intersection of all the things that you're not for the others, right? So this is, I mean, it's a bit fluffy maybe, but I think it's important to understand it.
Absolutely. Thank you very much. Very interesting answers, actually. In your opinion, which areas of study within the information and communication technologies hold the most potential for future researchers? Like, is there any emerging trends or groundbreaking topics that excite you and that you would strongly recommend young researchers explore?
So I just got a big center. I'm director of a big center for classical communication in the quantum era. And again, it's not for quantum computing, because it's just based on observation that whatever you do with quantum in the future, if you interconnect it, you have to have classical communication that supports it. And then the question we are looking now at is what will be the requirement for classical communication when you have quantum applications? That's one question. Another one is obviously the related to AI. I think now there is all this craze of AI training, which model is better and so on. The point is that when this starts to get deployed, you're going to have all these intelligent beings everywhere. And the question is how to interact with them, how to predict what they are doing, how to ensure trustworthiness and so on. So somehow now communication engineering is not that popular because people are developing these models. But when you start to interconnect AI models, then we might need a new type of network engineering, which is a network engineering for AI, right?
Yeah, thank you. And what key advice actually would you give to young professionals aspiring to build a career in academia or research? In your experience, what essential skills and qualities contribute most to success in these fields?
I think learning, I try to say this with a negative determination. I think trying to understand that building building a career in academia is a little bit like running a startup company. I tried startup company, it was not successful, meaning that you're starting from zero and you have to find funds, you have to pursue your ideas, and you have to get used to the fact that these ideas will be rejected, they have to try again, you have to redress and so on. So I think rejection and criticism is something you have to learn to cope in academia. I mean, what the reviewer two says to you, what the project officers are telling to you and so on. So I think it's important to do it, but it's also another thing which is very important is to learn that you have to try to decide what you want to do, define your area, because if you don't define, somebody else will do it for you. And then you're not working on your ideas.
Yeah, definitely. And I'm curious to know what first sparked or inspired your passion for your field, and how did you turn that interest into a meaningful career?
Yeah, I mean, I started to I decided to study telecommunications because at that time, because at that time, you know, communication was growing, beginning of 90s. I enrolled to university in 92. And this was a time which Ian would surely remember when Iridium was the name of the game, that we had all to have satellite phones, which are Iridium and everything will be connected and so on. And then in the end, it didn't happen like that. We got 2G, 3G, 4G, but Iridium and the satellites are back now. So I think two things which inspired me was satellite communication at that time in the 90s because it was popular, and also some very very simple thing because I you know at that time when I was decided to study in 92. I wanted to study something that has a lot of statistics and probability because that's something that was interesting me from we had the subject in high school that was very interesting and so on. And then I asked okay, what is the best engineering faculty that I can have statistics and probability? And they said, probably you have to study telecommunications. And that was it.
Yeah, thank you. My last question for you. Among your career achievements, is there anyone in particular, one particular contribution, whether professional or even personal, that has had a profound impact on you or others? And what makes this accomplishment especially meaningful to you?
Yeah, I mean, of course, you get it's important that somebody helps you at critical moments. And you know, as our common friend, Professor Liliana Gavrilovska, which Ian mentioned, which one that had a huge impact on me, also telling me how research is done, what publications means. You know, I've got familiar with IEEE from basically her, and and you know, this is a big impact that somebody shows you how things are done, what is the standard for high quality, which direction you should go, and so on. And then we also meet some very inspiring people along the way. I had the pleasure back in 2003 to meet Jim Massey, the information theorist, who, you know, told me some very simple things that said, you know, if you read these new papers in information theory, they're very complicated because they want to look complicated. But he said, we are engineers, we have to explain things in the engineering way. And, you know, that a bit turned, you know, this thing for me. I think there have been a lot of people along the way, you know, that believe in you and help you in the right moment. So I think we should always be grateful to them.
If I may add, Jim Massey was professor at ETH in Switzerland to Alessia, and unfortunately he passed away. So it was one of the great people in the information theory.
Exactly.
Well, thank you so much both for sharing. Thank you very much, Petar. There was a very interesting wisdom corner in addition to your excellent technical presentation. So Jana, closing words from you.
Again, I thank you.
See you all online soon.
Peter, I thank you. It was excellent, really. And I knew that's why we invited you. So thanks a lot again, and enjoy the time. And I hope to see you in June at BalkanCon. Alessia, we have the next speaker. It's in March.
Yeah, in 2 weeks. In 2 weeks, we have Professor Contact from Michigan University on the 18th of March. Yeah,
this is totally, you know, a very exciting area. It's, you know, from the health industry, molecular communication. And Chris is an old longtime friend of mine from his Stanford times. He's a pioneer really in cell communications. I'm not talking about our telecom.
No, I know.
It will be a very, very exciting talk. And he is running a huge, big center in Michigan State after he retired from Stanford. So we look forward to seeing you and all the others again. So we'll continue our success. Thanks a lot again.
Thanks a lot for inviting me. It was a pleasure.
And also,
thank
especially,
you very much.
I really thank you, Peter, for mentioning Liliana, because it's very important to appreciate your teacher, your mentor. That's very nice, and I'm really touched by that, and I will let Liliana know about it. She's really a fantastic lady, by the way.
I met her too. Yeah, I had the pleasure to meet her.
Yeah. Okay, thank you. And
thank you. Thanks a lot. Thank you. Bye. Bye-bye.
Thank you. Bye-bye.